Okay, so last time I guess we stopped at this point, age detection.
So
We
couldn't see this.
you don't see the slides.
There's a solution for that.
Last time we started talking about age detection, and then okay, so we said that age detection is something that we are going to do, and first before we start talking about age detection, let's define the meaning of the ages. Well, intuitively, age means that it is the boundary of an object, right? When you found the boundary of the objects in your images, then you have lots of information about that object. That's what we like to find, but in image processing, ages are defined in a different way. We say that, okay, we define the edges as sudden changes of intensity around an image point. For example, if you look at this image, okay, this color image, sudden change of intensity happens around these fence curves, right? Around the mouth of this person, between the fingers, like that. Okay, so these are the places where we see the sudden change of intensity. I mean, if you think images as 2D matrices, so when you say if there is an edge around here, it means that okay, around this position along this curve, maybe the matrix changes, the values changes a lot. So because I know that this part is dark and other parts are not that dark at all, so I would say the edges are around here. The same thing is here, so edges are both here. I can't do it exactly. Let me try to make it a little bit. So edges are both here at one side of this fence and the other side of that fence. Both of them, right? So that's the definition of an edge. That's why for this image I get these kind of edges, and sometimes I don't get any edge at all for some of the parts that we expect. So this is the result that we are willing to accept, and I am not saying that after finding the edges you are going to find your objects. We are not saying that, but that will give us lots of information about the objects. Okay, so edge detection is one of the first things that you can do on your images. Before I forget. Okay, that's what we are going to do. So these kind of things happen. Sudden change of intensity can happen at many places. For example, like consider such an image. Well, it's not an image, it's a drawing, but consider it as an image. These kind of intensity changes at many places, some of them are here. For example, one of them is, this is the shadow of the bottle, right? This box, this bottle has a shadow on the table like that. So you will say there is a sudden change of intensity around this place, the illumination discontinuity, we call it. So it doesn't show you any boundary of the object, but it's the boundary of the shadow. Shadow is not an object, but I will get an edge for there. Okay, around these writings, around these letters, you will see edges. They don't correspond to any objects, but they are just the changes in color discontinuity, surface color discontinuity. Sometimes I get edges for the depth discontinuity. I mean, the depth of this point is very different from this point, right? So that's why when you get the edges around this line, okay, when you get the edges around that line, that correspond to depth discontinuities, and in fact these kind of discontinuities most of the time correspond to object edges. And sometimes on the same object you will see edges around these kind of contours, right? These kind of contours. Okay, the both sides of that contour it belongs to the same object, but their surface normals are different. I mean, the surface normal is here towards the top, and surface normal is here towards the left. Okay, so the same object, but I am getting an edge out of those. So just to tell you that we are going to get edges for those kind of places. Edge detection doesn't mean that you're going to detect the object boundaries when you do the edge detection. Okay, so people have been doing edge detection for a very long for a very long time since the connection of the cameras to the computer world. We are doing edge detection, and when you do the edge detection, how do you compare your results with the other people's edge detection results? Becomes something. This is how we measure it. You measure your results, for example. Okay. This is a picture, obviously, an image from a camera. You ask 4 or 5 people to trace the edges of this image. Okay, they trace it like this. Okay, so there is maybe 90% agreement between the persons. You see, they are tracing those edges differently. How many traces I see? 1, 2, 3, 4, 5. I think I am seeing it 5 of them, right? So they trace, when you ask them, trace the object edges on this image. So they trace the edge of this. What is this? Is this a, what kind of an animal is this? What do you call this? Tiger? Is this a tiger? Whatever it is, okay, it's a mammal. So they trace the contour of this tiger. Also they trace the contour of these 3 trees, okay? But when I make an edge detection using one of my algorithms, I get something like that. So people are not concerned about these nice edges around the patterns of this tiger, okay? Do the same thing here, okay? And do the same thing here. The humans are very different from what I am saying. And humans, they don't agree with each other either, okay? They don't agree with each other either. Sometimes for this kind of simple images, they agree more, but for complicated images, they don't agree much. So what are we going to do? We are going to do this. What is the difference between the edges that we think they are correct and the edges that we think the edges that we recover from our algorithms? And this is the classification chart of that one, okay? So let's say I have detected the edges and I have the ground truth edges. Ground truth means that I accept these edges as correct edges, okay? So let's say ground truth is this set indicated by this red circle. Results of our method RM is this blue one, okay, red one and blue one. In a perfect world, I expect the red circle and blue circle to be exactly the same. Okay, their centers are the same, their radius is the same, they are exactly the same, but we are not living in the perfect world. Okay, so there will be some differences. First, we like this area, right? We like this area. This red area is the area where whatever we say is correct, right? So we like this area. That area is the intersection of the ground truth and the results of our method. Okay? Intersection of ground truth and results of our method, which are called true positives. Okay? So that's the TP, true positives. And we like that true positive area. We like it to be as large as possible. Maybe I should color it green. We like green, right? Green is better than, okay? So I like this green area. And outside of this green area, I don't like, thank you. Did everybody sign the attendance sheet? Did everybody sign it? Thank you. You didn't sign it, just take it and sign it. How about this area that I am just marking now? This area is, okay, it is part of the ground truth, but I didn't detect it. Part of the ground truth, but I didn't detect it. Though that area are the false negatives, okay? False negatives. True is good, false is bad, okay? False negatives are, I said negative, there is no edge there, but in fact there is an edge there, okay? We don't like false negatives much, okay? So we don't like these orange colored place much. And then there is this other area. It is kind of, again, its kind of color is reddish, this area. This area says that, my method says that there is an edge there, but in fact there is no edge, so it is false positive, okay? And the rest of this plane are kind of, I like, and I am going to mark them as like this. Rest of this plane, right? I said that there is no edge there, and in fact there is no edge. The ground truth says that, yeah, there is no edge. So I like the green places. I don't like the orange and red places. That's why the green places are called true positives and true negatives, and the red places are called false negatives and false positives. False are bad, trues are positive. Okay, false are bad and trues are positive. And I define two metrics here. One is precision, the other one is recall. Precision is true positives over results of our method. And as expected, let's say I detected 100 true positives, okay, and result of our method detected 200. So out of 200 edge pixels, 100 of them are correct. So I have a precision of 0.5 or 50%. So we like our precision to be as large as possible. Okay? So, well, obviously it could be it cannot be more than 1.0, 100%, because true positives cannot be larger than result of our method, right? So the true positives are a subset of our result of our method. Okay, so it cannot be greater than 1.0, or it cannot be less than 0.0. So I like my precision to be as large as possible, as so close to 1.0. And the other thing is true positives over ground truth. Okay, true positives over ground truth, and it is this one. Remember, the ground truth is the red circle. Okay, and the true positives is this intersection part, the green one. And I like this to be again as large as possible, that the largest one could be 1.0. This is the recall. That's the recall, okay? So why do we have two numbers to, why precision is not enough? Why recall is not enough? Obviously, I like both of them to be large, okay? Let's look at this plane. Let's look at this plane. Let's say, let me use some other color. Okay, let's say I have this plane, and these are my ground truth edges, and I detected this. What is my precision? Tell me about my precision and tell me about my recall. What is my precision for this case? My precision is going to be 1.0. Why? Because true positives over result of our method will be 1.0. Whatever I find, whenever I say there is an edge, it is an edge actually, right? It's an edge. But how about my recall? That is the true positives over ground truth. It is like maybe my recall is maybe at most 0.3 maybe. Why? Because most of this red circle, I say them, okay, those are all false negatives, okay? So I don't like it. I don't like it this way, okay? So tell me another picture. In this case, the precision is high, recall is very low. I don't like this. So precision by itself is not enough to express what's going on with this. Let's try to just paint a picture, just the opposite of this one. That is, recall should be high, but precision should be low. How am I going to do that?
We can reverse the red and green in the first.
Yeah, why don't we do that? Yes. So let's say my green is like this, and my red is like that. Okay? So recall is going to be, in this case, recall is going to be, what is the recall again? Recall is true positives over ground truth. Okay? My true positives are all of them, right, inside this red circle. My true positives are inside this red circle. My ground truth is this red circle. Then in this case, it's going to be 1.0. But how about my precision? My precision is, the formula for the precision is this: true positives over results of our method. So true positives are results of our method is the red one, right? Very large. True positives are the green, the red part. Again, it's going to be around 0.3. Okay? So it is not that difficult actually to get P 1.0 or R 1.0. It is difficult to get both of them high. If you get both of them 1.0, that's perfect, and you will never do that, okay? In any machine learning application, in any this kind of artificial intelligence related application, you will never get 1.0 for both of them, because, well, these are all ill-posed problems, right? There is human involved in there. Humans say that this is that and this is that, okay? So they don't agree with each other. So the nice thing is you need to get them, both of them, to as high as possible. So these are our evaluation techniques, and we will come to these later to talk about either with the edge detection or with the corner detection or some other types of detection. We will see these. Maybe you already knew about this from your machine learning course or data mining course or some other course, just a simple review, and we are on the same side, okay? So let's talk about these edges again. Well, edges are, our images are two-dimensional, and we like to talk about two-dimensional world, but it is kind of difficult to draw two-dimensional edges and etc. So we like to talk about the edges in one dimension, later generalize these ideas to two dimensions, because drawing stuff in one dimension is very easy compared to two dimensions. So let's look at some of the edge types. So this picture, we are going to use this in our examples a lot, okay? So this is what we are going to do. We are going to take a single line of this image, such as this one, okay? And we are going to draw it like a one-dimensional signal. So 255 is the highest, 0 is the lowest. So it looks like from the left corner, we start with like 200. It goes like 200. Then when I come to this part, it drops a little bit. Then it drops a lot. Then it continues. It gets high. And it goes. When I come to this pole, okay, then it drops and it comes back high. And then when I come to this part, you understand what I'm doing, right? So it's just a one-dimensional signal, one-dimensional function. So if I maybe do that, okay. So this part corresponds to, I guess, this part. This part corresponds to here, and what? This part corresponds to that part, etc. You know this, so that's what I'm going to do. Just take a single line out of this image and show the edges like that. So my expectation is that my expectation is that there is an edge here, there is an edge there, edge. So on this image, maybe this pixel is an edge image, edge pixel, okay? These are all the edges, okay? That's what I am going to try to do. So if we draw these kind of one-dimensional profiles from our images, these are the type of edges that we expect. Sometimes if you follow a line, a horizontal line in your image, you see like a step function. Something goes dark, then suddenly it's bright. Okay, this is called a step edge. Sometimes this happens. You go steady, then you gradually increase your intensity. This is called a ramp edge. Sometimes a gradual increase and gradual decrease, roof edge. Sometimes there are spikes, like something goes up or down suddenly. Okay, suddenly. So whatever we develop, it should capture all of them, all of these kind of edges. Again, these are one-dimensional, but if you visualize in your eyes about the 2 dimensions, I mean, we get similar stuff. Okay, so basically, yeah. So this guy takes this part and zooms in, and let's say I am going to draw the same thing. Let's say this is my x dimension and this is my y dimension, and I am going to draw, let's say this is 255, 0. For the center line, it goes bright, then suddenly dark, then very dark, then it goes back up and does that way, right? So this is what happens. So I expect that, I would say that there would be a edge here, an edge, another edge, okay, on this line. Okay, that's one thing. Another one is maybe, yeah, here. It looks like if I take a line out of this one, it goes bright, okay, and it drops suddenly, and it kind of goes a little bit up, but not much. Okay. So again, there is a single edge in there. This is kind of weird. I mean, let's look at this line here. Let's look at this line. So all you have, if I like to draw it, all you have is this, right? And if you like to detect edges, and if you are very, very precise, maybe you are going to say that there is an edge. So it's kind of noise. These are all edges. Maybe we should ignore these kind of edges there, right? So these are the things that we need to be careful about. Okay. So let's look at this image again. There are this is if I look at this profile, that's what I am getting. Bright, then sudden drop and sudden increase. And as you see, it doesn't go from 255 to 0 in just one step. There is a gradual function, and it doesn't go from 0 to 255 in just one step. It just goes in a smooth curve. That's what happens. I mean, in real life, when you take an image from a camera, it behaves that way. There are no sudden jumps from 0 to 255. I mean, it just sometimes it is very steep, but it is not sudden. That's what's going to happen. So if I like to detect these two edges, what am I going to do? If I like to detect these two images, I mean, in mathematics, usually if we cannot think about anything, we just take the derivative, because taking the derivative is so easy. And think about it. I mean, if I take the derivative of this function, this is what I get, right? At these areas, the derivative is 0. There is a very sudden change around here and around there. So my derivatives will be very different from 0 at these two locations. Here my derivatives will be negative and large. Here my derivatives will be positive and large. But other areas like this place and this place, my derivatives are 0. That's what I get. So it looks like detecting the edges in our images means that we will take the derivative, okay, and wherever the derivative is high, the absolute value of the derivative is high, we call those places as edges, because our definition of edge is the sudden intensity change. Well, you might say that, well, this works very nicely in one dimension. How about 2 dimensions? Well, we will talk about the 2 dimensions later. Okay, it will just generalize very nicely, depending on your method, of course. Okay, any questions up to now? So I defined the edges, and then I gave you kind of an idea how we can detect the edges using the methods that we know, and we'll continue that way. And taking these derivatives will be done using the filters that we have learned last week. Filters. Remember the filters? Just linear operations applied on the images. And since they are filters, and since they are linear, we will take advantage of the linear filters to eliminate noise and that kind of stuff, and you will see the results. Okay, so how would you find these points when you take the derivative? You take the derivative, you know that wherever my derivative makes a peak, this point and this point, I know that there is an edge. How would you find the peak points of your derivative function? You take another derivative, right? You take another derivative. In that case, it's going to be like this. It's going to come like that. Okay. There is a drop, and there is a high, and 0, 0, 0. There is a high, and like that, and 0, 0, 0. These 0 crossings here will give you the peaks of your derivative function. So you take the second derivative. So your second derivative will give you the peak positions. Take the second derivative and find the positions where your second derivative is 0, but these positions are 0, right? Your second derivative, we don't like those positions. We are after the points where there is a 0 crossing, either from negative to positive or positive to negative. Zero crossings are important. Okay, so here is a line profile from this red line here. I think this is the real stuff. So it is at this point, okay, this point corresponds to this point, right? So it is both, the intensity is increasing, increasing, increasing. Where is this sudden drop? I don't understand this sudden drop. Oh, sudden drop is, okay, I guess this part is this part, right? Do you see what I'm drawing? Okay, let me try to. So this part here, this part corresponds to this part in the image, right? And I guess choose a different color. Yeah, this part corresponds to the pole, and this is the door, right? The main door. It goes like that. You know what? I don't like this browser at all. I am going to use my regular robot. This is both slow and okay, good. So yeah, good. Okay, so this is good. And if I take the derivative of this function, I get this one. So these peak points here, here, here, they will correspond to the edges. But how about these positions? How about this one, and maybe this one? I mean, they are different from zero, but are they sufficiently different from zero? How, especially these and these. So if you take the derivative and second derivative and make it zero and that kind of stuff, sometimes we will have to be careful. I mean, maybe we should say things like, how about this? Anything minus 0.1 and plus 0.1, anything about anything below will be regarded as edge, maybe that. So we are call it this threshold. The problem is, how do you determine that threshold? I mean, threshold will change from image to image and object to object, and on the same, even on the same object, same image, thresholds might be different. So we will look at this problem later. Okay, so good. But there are some problems. What are the problems? Taking the derivatives of images like that doesn't work from time to time. For example, consider this function like this. Obviously, there is an image, there is an edge around here. There is an edge around here, right? There is an image around here. But you see, when I take the when I take the derivative with a very, very fine step, you would get a result like that. Why? Because this is not pure smooth intense area. Okay, this is not a pure smooth intense area, so the derivatives will be high, and this derivatives will be high in there too. So finding the edge, especially very in a reliable way, will be difficult, and we need to find a solution for that one. So our solution is usually, smooth the image first with a Gaussian. So our signal will be like this. Apply this filter. What does the filter do? It takes the weighted local average of the region. So apply it to this image. I will get something like that. Well, as you see, the edge is there, but its slope is kind of, its slope is not that steep, okay? So it's kind of a smoother image now. But if I take the derivative of this one, I will get a nice peak in here. So the peak will be here, right? And that will correspond to this one. So usually this is what we do. Take the Gaussian of this image, smooth it with a Gaussian using this convolution operation, FG, and take the derivative of it, and the peaks will give you the correct edge place. Of course, how much of smoothing should I apply changes from application to application, and we are going to see. And some people say that, well, this is a linear operation. This is a linear operation. Why don't we take the derivative of Gaussian and apply it as a filter? So this is the derivative of a Gaussian. If I apply this to this image, I would immediately get this one. So what is the advantage of this approach? Instead of applying the Gaussian and taking the derivative later, directly apply this filter. What is the advantage of it?
In the first approach, we apply the whole image to think.
Yeah. Instead of doing two things, I am just doing just one application of this filter. So applying this filter will both smooth the image and then will give you the peak points. So that's good. That's why we like these linear operators, okay? You can combine them together instead of doing it one by one. You apply them all together and that will give you these kind of nice results. Okay? Both the derivative operator and the Gaussian operator at the same time. So this is two-dimensional in one. This is one-dimensional again. One-dimensional. This is in two dimensions. Okay. If I apply this operator, this derivative operator to this Gaussian, this is what I get. Okay, in one of the dimensions. And if I apply it with this filter, 1 minus 1, in the y dimension, I would get just the rotated version of this Gaussian operation. Okay, and if I apply, for example, that this filter on zebra images, this is what I would get. Of course, what are the sigma parameters of my Gaussian? It's a parameter again. If the sigma is just 1 pixel wide sigma, this is what I would get. 3 pixels and 7 pixels like that. Okay. So what do you see in here? In this case, I see stuff like, okay, this one is very sensitive. Even the facial hair of this zebra is kind of, the edges from those hairs is visible, right? Every detail is visible. Here we don't talk about much about the hair, but these kind of dominant low frequency features of the image is more pronounced. All the others are gone. Which one is more useful? I wouldn't say that this one is more useful than that one or the opposite. It depends on your application. I mean, if you are after general structure of this animal, then I would use a very large sigma. If I am after small details of this animal, then I would use a small sigma. Okay, it depends on the application, and some applications will require all of them. Some applications will require all of that information. 1 pixel, 3 pixel, 7 pixel Gaussians applied together, and we are going to see how we can use them at the same time. Maybe not this lecture, but next lecture. Okay, so we will come back to this one in a few minutes. This is how you take your derivatives again. We talked about this last time, taking the derivatives. So basically either you do the backward difference, forward difference, or the central difference. And for these are basically mean that we are running some features. Okay, good. Any questions? Okay, if there are no questions, let's take 15 minutes of break and let's keep the windows open. Let's be here around 15:43, 50 minutes.
Ya benim hazır da bir türlü gönderemedim ya. Bugün göndereyim.
Tamam, üzerine futbol sahası üzerine
Allah'ım geri dışarı çıkmam lazım.
yapıyor?
Yok makineci ya, makine falan.
Ha.
Ama ne yapıyorlar ya, bir bak işte.
Ben test üzerine konuşuyorsun orada.
Okay, so we know this. This is how we do the differentiation in the continuous world, but our world is not continuous. We live in a discrete world, so instead of taking this as a infinitesimally small epsilon value, we take the finite value. In our case, the simplest one, the smallest one we can take is just one pixel, and this will be our, these will be our operators for taking the derivative. And since we have two dimensions, not one dimension, I can take the derivative with respect to x, and I can take the derivative with respect to y. And if I apply this operator, I would be taking a derivative with respect to x, and if I apply this operator, I would be taking derivative with respect to y. And this is a sample result of the same image. This is the image input image. If I apply this operator, this kernel, this operator to this image, this is the result that I would get. And as you see, since this is this is more sensitive. This is sensitive to the changes in the x direction. Okay, as you see, I kind of there is a change in this direction at this position in y direction, but when I look at this image, I don't see it much. I don't see it much, especially around, well, since this is a diagonal edge like this one, it has both x and y components. I am looking for an edge, okay, like this one. This is mostly a vertical edge. For that one, I don't get much response. Okay, all the responses are kind of horizontal, the horizontal responses. But if I do it just the other way, the responses kind of changes. I get more response. For example, look at this one. This response is more than the other one. I don't have perfect. Yeah, maybe this is a good example here. You see this one? There is a very dominant edge detected because this is a vertical edge, and for the vertical edges I have this operator, but you don't see much around that part of the image for the y derivative. Did anybody say something?
Nose is same also.
Yes. What?
Girl's nose is right side.
Yeah, nose. Yeah. Well, yes, exactly. Again, the difference here is that I see this on the x dimension derivative, but on the y dimension, nose doesn't make any difference. So this is again, I mean, when you question for you, I think we talked about this. If I apply this operator to this image, let's say this is a grayscale image, the number change from 0 to 255. That's our assumption. That's what our assumption is. If we do it that way, and if I apply this operator to this image, that means that I am multiplying the numbers by 1 and minus 1, and I am adding them up. So the numbers are 0 to 255, all the numbers. So the smallest number out of this operator would be, if I multiply one of the pixels with 1 and the other one with minus 1, the smallest number would be, let's say one of them is 255 and the other one is 0. Okay, that's what happened. Okay, 255 to 0, it would be plus 255. 0 to 255, it could be minus 255. So my numbers out of this convolution operation changes between 255 minus 255 to plus 255. So that's out of my range. I can show images from 0 to 255. So I can linearly map these values to 0 to 255. Okay, 0 to 255. Let me use a comma. Okay, so linearly map it to this one. So that's how I produce this image as a visible image. Okay, these are x derivatives, these are the y derivatives. That's what I get. I mean, when you look at these images, you will say that so we are detecting edges, and I don't see any edges there. I mean, what is the purpose of the edges? You will say that, okay? You will say that these are the edge pixels. These are the edge pixels because there is a sudden change in there, right? These are the edge pixels, but these are not edge pixels. These are not edge pixels. So I need to classify each pixel either as an edge or not an edge. When I look at this image, all I see is just a regular image. The numbers change from minus 255 to 255. In this case, I normalize to be between 0 to 255. I don't see any classification of the pixels as an edge pixel or not an edge pixel. So what are we gonna do? Okay, we are going to apply some other steps, obviously, and we are going to see it in a few minutes. Okay, here one case is this. Okay, noise is making our job a little bit difficult. Why? Because if there is lots of variation between the pixels, very small variations, my operator is responding some big way for those variations. What are we gonna do for those as we did before? We are going to use again the Gaussian smoothing operator before we apply the derivatives. Okay, so there is one example here. Again, zebra image. I added some more noise, and if I take the derivative of it, you see this looks nice. Not that nice, not nice at all, right? So we need to apply some operator before we do this kind of a derivative operation. Okay, so image smoothing, that's what we are going to do. So I'm going to skip this one, and let's go to the direct edge detectors actually. Okay, so we are going to basically look at these three, 1, 2, 3 main classes of edge detectors. The second one is the one that you have suggested. You told me that I would take the second derivative of the image and look at the zero crossings of it. It's called Laplacian of Calcium, and we are going to see it. The first one is directly apply some operators and do some processing after that, and the third one is kind of a mix of these two, maybe. You will see. Okay, let's get the first one. Private and sober edge detectors from 1960s and 1970s. Very simple approaches for edge detection. This is what they do. Okay, I have two sets of classes. Nice. Okay, did I bring this one? Which one is better? This one is good. Yeah. Put this one back into mine. Okay, so you will take the image, okay, you apply this simple averaging filter. It averages the image in, again, in y dimension. Then you apply this filter, central differencing operators, 1, 0, minus 1. So smooth it, then apply the filter. Why don't we do it at the same time? So let's apply this one on this one. Okay, matrix multiplication. 1 times 1 is 1, 1 times 0, 0, 1 minus 1, and do it 3 times, and you get this nice filter. So apply this filter to get the edges in direction, and apply this one. Again, this one is with the derivative is in the y direction. Okay, smoothing is that way, and this one will give me edges in y direction. Okay, That's called the private edge detector. Sobel says that, well, let's do the smoothing not like equally smoothing, but more smoothing, more weight for the center pixel, okay? And you get the results like those. That's the only difference between private and Sobel. And after that, this is what we do. Take the gradient with in x direction, take the gradient with y direction, okay? You get two images, right? X gradient image and y gradient image, and take the geometric normal of these two. There's the magnitude of these two images, and that's going to give you the magnitude of the gradient. So basically, this is your image. For each pixel, you produce this x gradient and y gradient, and then take this value, and let's say this is x and this is y, and I make a new image by doing this x squared plus y squared and square root, and put it inside this image. Okay, that will give me the threshold. That will give me one image, and I will apply a threshold, and I will get the edges. Okay, the same input image, x dimension gradient, y dimension gradient. Okay, square them, add them up, and take the square root. Okay, this is the magnitude image. Okay, so the 0 means that no changes either in x or y dimension. 255 means that there is a very large change either x or y dimension, I don't know which one. And apply a threshold. For example, if your value is above 100, then those are the edge points, and this is what you get. So how many parameters do we use for this algorithm? How many parameters do we use for this algorithm? One parameter is this threshold, right? We need to make a decision. I mean, what is my threshold value? 100 or 50 or 200? I don't know. That's one parameter. Maybe the other parameter is the amount of smoothing before you apply these two operators. Okay, but it looks like I have already decided that for Sobel, okay, it will be the smoothing operator. For private, this will be the smoothing operator. So it looks like only a single parameter for this simple edge detector class, Sobel and private edge detectors. Do we like the results? Well, not much, right? So it has lots of false negatives, lots of false positives. And the bad thing is that, let's look at this nose. I would expect that only a single width pixel line has to be detected like edges, but it looks like for the same edge, I have 1, 2, 3, sometimes 1, 2, 3, 4. Yeah, 4. Is that 4? Maybe 5. 5 pixels are marked as edges. Okay. I mean, there is a thin edge in there, like this one maybe. There is a thin edge in there, but it is marking lots of neighboring pixels as the edges, so I don't like it much. And I lost many details around. Remember these fence edges, they are all gone. So you might say that, why don't we lower our threshold? Maybe we are going to get them, right, like that. But if I lower my threshold, then I am going to get lots of false positives around this part, right? So, well, I mean, this is 80s technology. It works like this. Well, I mean, to begin with, this is a very difficult image to work on for the edge detection. But, I mean, it's a good image to kind of show you what kind of problems we would have for real life images. Okay, so that's the first class edge detection techniques, Sobel and Prevet. Basically, they have their own kernels. This is the for Sobel Ix and Iy operators. You apply these for the, so maybe I should call them Sobel X and Sobel Y. Sobel X and Sobel Y, and they will give you these ones, and you take the magnitude of them, and yeah, so for each image point you get two-dimensional gradient value, and with the two-dimensional gradient value you get the magnitude, and that's your result, and apply a threshold. We don't like the threshold much. Let's do something that is different from the threshold. That will be our second class of edge detectors. Okay, so we will smooth the image by a Gaussian first, get rid of some noise. Okay, then apply Laplacians to S. What is Laplacian? We are going to see and find zero crossing. Laplacian is this. Okay, this is our Gauss kernel. This is our Gauss kernel. Laplacian is the second derivative of the Gauss. Okay, so this is our Gauss kernel applied to image. I will get a smoothed image. On this image, take the derivative of the derivative. Okay, this is called Laplacian, like it is shown like that. And if you take the instead of taking the Gaussian filter of the image and applying to the resulting image, why don't we apply the second derivative operator to the Gaussian itself and later apply the resulting operator to the image? That's what we are doing. So if I apply this Laplacian idea to the Gaussian directly, this is what you would get. Okay, take the second derivative of this Gauss. This is what you would get, and that's the shape of it. Remember, the Gauss is like a cap. This is like an inverted Mexican hat, right? It's like a Mexican hat, but it's inverted. So apply this to your image, and all the zero crossings out of this one will be your edge points. Remember this. If this is my step edge, if I take the derivative of it, you will get something like this. To find the peak points, I apply a second derivative, you will get something like this. I am after this zero crossing point. Okay, so image, first derivative, second derivative, and your results. Here, in this case, if this is my original image, with lots of noise, I like to apply a Gaussian filter first. After the Gaussian filter, first derivative, second derivative, and find the zero crossings. With the Laplacian of the Gaussian, I am doing three things at the same time. Apply the Gaussian, take the first derivative, take the second derivative, and then find the zero crossings after that. Okay, this is called Laplacian of Calcium. And well, after that, what are we gonna do? After that, okay, this is one Gaussian, just one dimension. This is our X, and this is the Gaussian at the center, see? Okay, it looks like if this is our X, Gaussian is like that, around 0. And then in 2 dimensions, it looks like this. See, at the center, it is the largest, and like a circle, like this. And see, and when I do this, when I do the largest one, okay, it gets smaller and smaller and smaller with sigma value of 2. This is a 2D Gaussian, the 2D Gaussian. And if you take the second derivative of it, okay, this is what you would get. This is the numerical representation of the Laplacian of Gaussian, second derivative of Gaussian actually. See, at the center it is the deepest, just the inverted Mexican hat, remember. If I draw the Mexican hat it would be like this. it would be like that, and these are my coordinate systems. At the center it is the smallest. If I go this way, it is get largest, then it drops. Okay? Inverted Mexican works that way. Okay, after that, you scan the lines and the columns one by one and find these kind of zero crossings. Let's say I applied this, okay, I applied this log filter to my image, directly to my image, and you get results. Then you start scanning your resulting log, image like this in this direction, and find the places where there is a transition from positives to negatives, negatives to positives, positive to zero to negatives. Okay? So find all of them, and after that, for example, let's do some example here. Let's say here I have 5, 0, minus 5, 0, 25, 35. Okay, and maybe 6 here, maybe 6 there. Okay, so let's find the zero crossings. Let me show you the zero crossing. There is no zero crossings here, no zero crossings. I have seen a zero crossing here. So it goes from minus 5 to plus 5 to minus 5. Okay, is there an edge here? I will make a decision by looking at the slope. From plus 5 to minus 5 in 2 steps, in just 2 steps, so it is like 10 over 2, right? 10 over 2, so its slope is 5. And then here from minus 5 to 25, very steep edge maybe. Okay, there is a zero crossing again, and it's going to be 30 over 2, 15. Okay, the slope of the zero crossing is 15 here and 5 there. This one says that, okay, slope of the zero crossing calculated, okay, and apply a threshold value to the slope, and that will give you the edges. Okay, that will give you the edges. Another threshold here, but this time we are not as sensitive as the Privet and the Sobel operators for those. Okay, slope of zero crossings. That's the last part of this edge detection method. It's very simple actually. Apply this operator. Of course, there is a parameter here like sigma. What kind of sigma do you want? You want a large sigma or small sigma? How much smoothing you want to apply to your image? That's the first thing. The second thing is your parameter about the zero crossings. Okay, and these are some results. Let me show you some results on this one. Okay. See the difference between the results of the Sobel Privet operators and the log operator. Okay, so you get lots of edges, and most of them are the places that we wanted, especially the ones about around the edges, and I get this nice, okay, vertical one, and some from the shape of the face and the nose, remember those, okay, and these are the shapes of the fence and etc. But lots of false positives too. Okay, lots of false positives too. We have to find a way of dealing with them too. So that's the idea of Laplacian of Calcium operator. Simple technique, lots of mathematical background, lots of mathematical justification for this technique, and it works nicely, but you need to choose some large sigma parameter for that one, because taking the second derivative of an image is very sensitive to noise, okay? If there is lots of noise in your image, then the first derivative will be sensitive. Taking the second derivative will be even more sensitive. That's going to be bad, okay? Another nice thing about this operator is this. Remember, we like Gauss smoothing previously, if you remember this, because Gauss is a separable operator. What do I mean by separability? It means that instead of applying a two-dimensional kernel to our image, we can apply two one-dimensional operators. This is an operator in x dimension, this is an operator in y dimension. Apply it 2 times, this one and that one. That will give you less number of multiplications. So two-dimensional Gaussian filtering, if I have n pixels in my image, it will be proportional to n square, n times n. But if I do one-dimensional the convolution, it will take me 2n multiplication. So the difference is very large. Okay, the difference is very large. This is much more efficient than 2 dimensions. That's why we like this operator. But the noise is the main problem with this operator, because taking the two derivatives one after the other one will amplify our noise, and that's not going to be good. If I can show you. It's gone. Was this the reason why I switched to the other viewer? Okay, let me start from this one again. Maybe I need to update this application. Maybe there is a... Okay, so zero crossings will give me this. So remember, the first parameter is the Gauss, the sigma value. If sigma value is 1, this is what you get. Sigma value 3, this is what you get. Sigma value 6, this is what you get. Okay? So you are going to ask, which sigma should I use? Well, again, it depends on your application. Sometimes there are techniques that use 3 of them together. Okay. So this is the second set. This is the second type of edge detector that we are going to talk about. Let's look at the third one, which is the one that we use most often, which is the okay, Kenny edge detector. Okay, Kenny edge detector says that there are 3 things that you need to be careful about when you are doing the edge detection. First, okay, you should be robust against noise. Noise should not affect your results. Second, when you say there is an edge, it should be at the correct place. The third one is you shouldn't report too many edges around the edge point. Okay, so it makes some observations about these 3 problems and offers a solution for you. Okay, there's poor robustness, poor localization. Usually it happens with noise, and we have to handle the noise. And unfortunately, taking second derivative doesn't make these 2 problems better. It makes them worse. So can we say that I will take only 1 derivative and I will continue the rest myself? That's what Kenny is going to do. This is the guy Kenny from 1980s. I don't know, maybe 1990s. Okay, so these are the steps of Kenny. First, smooth the image with Gaussian. Okay, then compute the derivative in x and y dimensions separately. And like the previous operator, find the magnitude, x squared plus y squared stuff. Also find the orientation of each pixel. I am finding the magnitude of each gradient point, also find the orientation of each point, then apply this non-maximum suppression, okay, non-maximum suppression to get rid of these problems, okay. So I am going to select only the center ones, the other ones will go away, and then finally I will apply the hysteresis thresholding. Well, it looks like we will never get rid of the thresholds. Somehow we have to apply thresholds. Can you say that by choosing two thresholds instead of one threshold, our results will be more robust? Okay, so we are not going to say anything above 100 is my H pixels. We are going to say a little bit different things. We are going to say I have two thresholds, 100 and let's say 50. Okay, anything above 100 is very strong. I will take that as an edge, but anything about 50 that are connected to the pixels that are above 100 will be taken as edge pixels too. So if you have a very strong neighboring pixel that are considered as an edge, then I will consider you then as an edge too. So that's called the hysteresis thresholding, and we are going to see that. Okay, so it looks like this step and this step and this step maybe are very familiar. So we are going to spend some time on number 4 and number 5. So first, smoothing, we already know that. Okay, smooth the image with the Gaussian. So sigma is one of our parameters now. Okay, smooth the image with a Gaussian. So smooth, after the smoothing, take the derivative. That's what we are going to do. So maybe I should take the derivative of the Gaussian in x and y dimensions and apply these operators. That's what we are going to do. Okay, so we are after finding the x derivatives and y derivatives of the image. Remember, like the Sobel and Prewitt, that they have built-in smoothing effects inside their operators. Kenny says that, okay, I'm not going to do that, but instead of doing that kind of a smoothing, let's smooth it by using the Gaussian in x and y dimensions. Okay, so Gaussian, take the Gaussian's x dimension derivative, y dimension derivative, two of them. I have two operators now. Apply these two operators to your image. Okay, this is what you're going to get. You will say, well, this is very similar to what Prewitt and Sobel did. Yeah, that's true. But this is more mathematically robust. Why? Because I'm saying that I'm using Gaussian smoothing to smooth the image, and I can adjust the smoothness amount by turning the sigma knob less or more. Okay, so I have these two images, and after that, like the Prewitt and Sobel, calculate the magnitude image. This is the magnitude image. Okay, similar to Sobel and Prewitt. Remember, Sobel and Prewitt applied the threshold on this one, called whatever remains above the threshold as edge points. Kenny doesn't do that. Kenny say that also calculate the direction of each point. He says that, okay, so the magnitude is very high here because there is a strong change in the x and y dimension. That means that the direction of this edge is like that, okay, and here the direction of the edge is like this, and here the direction of the edge is like this, right? So for each point, I calculate the direction of the edge. Direction of the edge is calculated this way. As y over as x, that's the division, okay? And if you take the arctangent of it, okay, just the inverse tangent of it, you will get the direction value. I think I had a nice picture here. If this is my original image, okay, this is the x direction filter of the Gaussian. Just take the x derivative of the Gaussian, y derivative of the Gaussian. These two become my filters, and I apply them on the image. Okay, x derivative, y derivative. This is the gradient magnitude. Remember, it's like x squared plus y squared square root, and then this is the orientation image. That is sy over sx and tangent minus 1 arctangent. Color means it is the angle. I guess red means 180 degrees and green means maybe 90 degrees. Here 180 and 0 are the same thing. 90 and 270 are the same thing. So it is not direction sensitive. Well, I mean 0 degrees and the 180 degrees are the same thing for this picture. So as you see, this part, this red here and this red, okay, they are the same thing also. But yeah, well, let's look at this part, this blue and this blue. Well, it's kind of purple, but anyway. So color shows you the direction of the edge. Okay, for most of this image, everything is black. It is black because gradient magnitude is very low. For those parts, I didn't show you the orientation. There are usually better images on the web. Let me show you orientation. Well, okay, gradient orientation image. Maybe is this a good one? I need something colorful. Let me go to images. I am going to find it. I am going to find something color. Yeah, maybe this one is a good one. Yeah. So they take the obviously this is a fingerprint image, right? If you try to find the edges on a fingerprint, okay, there are lots of edges, but their orientations are very, very different. Okay, so the color kind of shows the orientation of it. As you see, the greens are kind of 135 to 285, right? Reds are kind of 90 degrees. Is it 90? Yeah, 90 and 270 maybe. No, well, reds are horizontal, both going up and down. Purples are this way. See, this is the orientation. Shows you the orientation. Shows you the color. Color shows you the orientation. Maybe the other way around. But this one is not, again, is not direction sensitive. I like to find something direction sensitive. Couldn't find it. As always, if you try to look it up, gradient orientation image with color, I get the same thing here. Yeah, this one might be it. Is this a better one? No, not that good. I think the better one is this one. Okay, so different directions are marked with a different color. The arrows going this way are pinkish, and arrows going this way are bluish, and these are going down. And are there any? Yeah, this one, these are going down. Anything going up? Couldn't find it. Sorry. Well, I mean, you have to take my word for it. So the color shows you the direction. That's our second image. So the first image is the gradient magnitude. The second image, our direction. So for each point, okay, for each point on this image, there is a direction indicator like that. It is showing you where to go to a lower pixel, or the dimmer pixel, or the low intensity level pixel. Okay, so for each point I have that comes from the color image. So what are we going to do? We are going to use those two images for non-maximum separation. Let's say I have an image like that. In this image, this part is dark and the rest of it is bright. So if you take the gradient of this image and take the magnitude, this is what you're going to get. Okay, around this part, you would expect the edges, but because of the smoothing, the gradient magnitude is very large around this edge of the circle, edge of the disk, and the rest of them the gradient is very low. My purpose is, okay, find the edge points like this. You are going to say, these are the edge points. Okay, if I take a threshold, most of these pixels will stay out above the threshold, but my detected edges will contain lots of false positives. I don't want any false positives. This is what you're going to do. I will take this pixel, for example, this pixel, maybe make it a green one, okay, and I will walk along the direction of the gradient, along this line. Direction of the gradient is like this, is like that, right? Is like that. Direction of the gradient. And while I am walking on the direction of the gradient, I will try to, let's look at this line, this green one, okay? Let's try to draw, okay? This is my X, maybe I should call it K. This direction is K, okay? While I am walking on K, okay, I am drawing the magnitude value, so it's going to be like that, right? So this point corresponds to this point. So if I walk along this line, over this line, I try to locate the point where the magnitude is the highest. Okay, so I will walk on this line, and I will say that my edge cannot be this point. Why? Because the other point is larger than that one. My edge cannot be this point because this neighboring point is larger than this one, and larger than this one. When I come to this position, I will say that, okay, well, around my neighborhood, I am the king. So I must be the edge point, right? I must be the edge point. That's what we are going to do. So that's why this is called non-maximal suppression. You will say, am I the maximum? No, then I am suppressed myself. I am going to suppress myself. I am just eliminating non-maximal points. Okay? So for each point along this line, I am doing this one by one. At the end, only the maximal point is going to stay, and that will be the highest magnitude point. Remember, this is not a two-dimensional search, just a one-dimensional search. I am doing this one-dimensional search on the gradient direction line. There is only one gradient direction line. It is this line or that line here, right? Okay, so this is a one-dimensional search, and with this search we do the non-maximum suppression. After doing that, this is what you would get. So I suppressed all the non-maximum ones, and as you see, I get this nice thin edge chain like that. Another edge chain is here, and another edge chain is there, right? Like that. So doesn't matter what kind of magnitude you have, it will give you lots of edge chains, and most of them are very meaningful. You see this one? It goes like that. Some of them are very, very faint because their magnitudes are very low, but they all make sense. So intrinsically you would say, let's apply a threshold to this one. For example, any magnitude larger than 25 are my edges, and binarize this image like that one. But Kenny says that no, we can do better than that. Let's not use a single threshold. Let's use this information. For example, if you apply a single threshold, you have lost all the neighboring pixels in this chain, right? Like that one. It was going this way, and because rest of the elements in that chain, since they have a lower threshold, lower than 25, they will go away. Let's not do that, okay? Instead, choose two different thresholds, 50 and 10. Anybody above 50 is a good edge. But if you are in a chain, let me do this, okay? If you are in a chain, I know that this part is good because they are all above 50, but these are all connected to 50, and they are about 25. So I will consider them as edge pixels. So your neighbors, your connected neighbors are kind of saving you from elimination. Okay? So you might be a low magnitude edge, but you are connected to a high magnitude edge point. Okay? If I know that, then I will keep you in. That's called hysteresis thresholding. And after okay, it's like this. I have an edge chain. It does that. Okay, below some gradient magnitude, they are very, very weak edge gradient magnitudes, but they are connected to very visible edges. So I will follow this chain, I will make this process, and at the end I get this. These are regular private type, regular single threshold result. And this is a two threshold result, low 15, high 35. It looks like I eliminated lots of noise, like that one, but I kept lots of nice edge chains too. Okay, so this is what Kenny edge filtering does with the hysteresis thresholding. So two things that are important for Kenny. Okay, one is the non-maximum suppression. Eliminate all the pixels in the same neighborhood along the line of the image gradient. Okay, that's called the non-maximum suppression. One-dimensional search. The second one is the hysteresis thresholding. Okay, so how many parameters do we need for this, Kenny? One parameter for the Gaussian sigma. Okay, then we apply the derivatives, and then non-maximum suppression doesn't need any parameters, and I need two parameters, hysteresis low and hysteresis high, and three parameters will make us a nice edge detector. Okay, it doesn't take the second derivative of the image because of the noise issues. Instead, it uses this non-maximum suppression plus the hysteresis thresholding. Good. Well, I used too much time for this lecture. Let me take some break, and after we come back, Let me show you some functions from OpenCV that will take the image, that will find the edges of images, and after that we will continue with our next topic, which is the corner detection. One level up in our pipeline of the image processing. Okay, any questions so far? Okay, hold on to your questions, and when we come back, I'll get your questions. So let's be here around 16:49.
Lisans var mı?
Lisansım.
Kendi aranızda WhatsApp grubu var mı ders ait?
Evet var.
Ya biz de yüksek lisans grubu kurmuştuk ama hani çok fazla kişi olmayınca size bir soralım dedik. O grubu bir yerde paylaşabilir misiniz bize katılsak ya da?
Şeyde 3. sınıf grubunda var mısınız? 3. sınıf grubunda geçen hafta biri paylaşmıştı da.
Yok, ben sizden numarasını alsam, hatta numaramı versem beni ekleseniz ben size de paylaşırım.
Lisans kurduğunuz belli oldu.
Evet, o da olabilir. Bu grupta kaç
Tavsiyelerimi
kişi olduğunu
isterseniz.
Bu grupta 24 kişi var. Bizde daha fazla kişi varsa biz
Yok,
böyle
bizde yüksek lisans 4-5 kişi var.
yapıyoruz.
Machine learning alan varsa yine lisansta, onun grubu var mı?
Onu almıyoruz.
Hani,
Ama var grupta.
sen alır mısın? Tamam, ben
Olayı anladım.
seninle paylaşayım. Yarın sabah machine learning'de de yine lisans arkadaşı arayacağım. Varsa gruplar birleştirelim, bir şey yapalım çünkü çoğunluk neredeyse orada
Burada da
toplanıyor.
kimse bir şey yapmıyor çünkü ama numaramı vereyim.
Tamam. Yani biz geçen senelerden beri böyle hep şey yapıyoruz. Gruplar üzerine haberleşiyoruz. İyi oluyor. 500.
Ne 35? 426. 94 70 olur. Evet,
Ben küçük grubu kurdum ama işte diğer insan öğrencileriyle olan gruplarla bir araya gelirsek daha iyi olur. Kapalı konusu daha iyi olur.
Bu kadar soğuk hava hatırlayan var mı ya İstanbul'da? Görünüyor böyle yani. Mart'ta olsa bu biraz fazla ya. Bu Sivaslı olarak konuşuyorum ya bir yanlışlık var bu işte. Okay, so these are the steps of Kenny edge detection. So non-maximum suppression, making a search along the gradient direction, and after that doing hysteresis thresholding is something that Kenny added to the literature of the edge detection. Okay, so this is the basic thing. So for xy, I know the direction of the gradient. Okay, I know which way the image gets brighter and image gets darker because that's the gradient, that's the mean of the gradient. Okay, so I compare this image point xy with its two neighbors. If I am higher than both of them, then I am the king. Otherwise, I suppress myself. I say that I have a neighbor whose gradient is higher than me, so I will not talk after that. Okay, so that will guarantee that only one pixel will be selected out of my neighborhood, and that will be representing my neighborhood. And I'm going to do this for all the points in the image, and these are the results. Okay, so when it comes to the thresholding, I have a high threshold and low threshold. Okay, anything above the high threshold is an edge pixel. Anything below the low pixel is not an edge pixel. In between, I have this rule. Okay, if I am in between high and low, but I am connected to a high pixel, then I am an edge. Otherwise, I am not an edge. Okay, that's the connected component analysis. So I scan the image from left to right, top to bottom, doing this hysteresis thresholding, and these are the final results. Okay, before non-max suppression, and after the non-max suppression, and after that, these are all the, okay, non-max suppression doesn't eliminate anything based on their threshold values, okay? Everything is there, okay? So see, these are all very nice thin edges. Very, very thin edges, 1 pixel wide, okay? Which ones are the edges and which ones are not the edges? I will make that decision based on the hysteresis thresholding, and this is the hysteresis thresholding result. Okay, I don't know the threshold values, but as you see, results are not bad. Okay, so the Kenny has a few parameters. One of them is the sigma of the initial Gaussian. If sigma is 1, these are the results, and sigma is 2, these are the results. Let me show you our OpenCV documentation. OpenCV edge detection. Okay, documentation is here. Good. Let me show you. Okay, these are all edge related stuff. Let me, where is, maybe, okay, let's look at the Kenny first. So Kenny says that you give me an image, I will give you the edges. I need 3 things. One of them is the threshold number 1, hysteresis threshold, low value, high value. This is the aperture of the width of the sigma that I'm going to apply, and this is the gradient. How do you calculate the gradient? L2 gradient or what? F flag, okay. If you like, this is the default one. This is the one that I showed you, L2 norm. If you like to calculate your gradient using this one, then you are going to make this false. Okay, this flag, false. Okay, this is L1 norm. Sometimes it is useful, I don't know there. Okay, so this is how the Kenny edge detector works. Let me show you the LOG edge detector. Are there any? Okay, do we have maybe LOG? These are the logarithm stuff. Okay, let me go back and go back one more. And open CVH detection. I don't want to see Kenny. I don't want to see where is. Do you see edge detection? Learn open CV. Is it a good one? Usually they talk about Kenny with this kind of stuff. I couldn't find it. Maybe. Okay. Open CVH detection. LOG operator. These are all Kenny. I couldn't find it, but I remember there is Laplace of Calcium edge detector somewhere. Concept of Kenny edge detection. Image processing. Edge Kenny. No, I couldn't find it. Sorry. Only Kenny is available for now. I don't know where the others are gone. See, there is this Sobel is here. Okay, Laplacian is here. Okay, good. So this one says that find the Laplacian function, calculates the Laplacian of the source image by adding up the, see this one? It finds the Laplacian of the input image, right? So it takes the second derivative of it, and if you provide a Gaussian to it, it's going to find the Laplacian of the Gaussian. That's going to give you a filter, and you can apply that filter using the filter convolution techniques that we have learned using the OpenCV last week. Okay, so good. So you read the OpenCV documentation. Zero crossings. Let me find that one. I remember there was a function to find the zero crossings of. Okay, go there again. Zero crossings. Yeah. This one. OpenCV doesn't talk about OpenCV. Well, let me open it, and then after that I will immediately go back. Original image, difference of Gaussians, doesn't use open. Well, it uses the OpenCV, but it doesn't. Okay, input. Convol to the LOGC. It doesn't have a perfect LOG based edge detector. It just applies the LOG kernel, and LOG kernel is given like this one, but I can calculate using the LOG function of the OpenCV. It applies it using the convolution. I get this image back, and after that it tries a zero cross detection function, and it handles all the zero crossings, and these are the edges. Okay, so I guess that will be it for the edge detection. I will now start talking about corner detection. Are there any questions? Let's look. Yeah.
In what kind of applications do we have to use edge detection?
Where do we use the edge detection? What kind of applications we use the edge detection?
Yeah.
Well, usually, I mean, if we are talking about the 80s and 90s, everything has to be done by the edge detection. Later we started doing stuff like this. I detected all the edges in an image, and all that edge information is going to produce me data about the signature of the image. So I get the edges. If I look at the edge orientations in an image, okay, that will give me information about the type of the object contained in it, okay. So maybe I can feed that information to a machine learning application, and that machine learning application will tell me that, okay, there is a dog in this image, or there is a cat in this image, etc. So you usually don't use the edge detection results directly, saying that if I have this kind of an edge, then this is it, and if I have this kind of an edge. So usually these are in vision processing, okay, you start by doing very simple stuff on your images that will give you a little bit more abstract information about your image. Using this new data, you apply other kind of techniques, so you get more abstract data about your image. And at the end of this pipeline, you hope to get very, very abstract level of data, such as there is a projector in this image, there is a computer in this image, kind of thing. So edge detector is usually the first level of processing. Okay, so don't expect very meaningful results out of this edge detection. And we are going to go one level up, which is the corner detection. And again, nobody does the corner detection and would call this the end result of my image processing or computer vision task. You usually use that information in somewhere else. Okay, so we are kind of working towards that destination. Okay, so maybe at the end of next week we will do the image stitching. Okay, what is image stitching? You take the 1, 2, 3, 4, 5 images of this classroom, and you do the stitch the images together to make one large image out of all those. To match all those images, you need to do the corner detection, and corner detection is built on top of the edge detection. That's why we are talking about it. Okay, so that's a good question. It is always good to think about why are we doing this? Why are we talking about it? So especially before learning that stuff and after learning that stuff, ask that question: why am I taking this course? And after taking this course, why did I take this course? Why did I come to this department again? So those are good questions. And some of them I don't know. Okay, let's look at this again. Corner detection. Okay, here is corner detection, and let me get rid of my annotations first. Okay. Harris corner detection, like Kenny, Harris is another guy that invented this corner detection technique, and we will be interested in this shift actually. Okay, you remember this Laplacian of Calcium? We did well. I mean, I'm going to skip this one, but with the Laplacian of Gaussian, we can do this kind of interesting. Okay, remember that with the Laplacian of the Gaussian, you have the Gaussian sigma. Also, the contrast is the slope of the zero crossings. If you play with that kind of stuff, this is what you would get. It looks like this is the better one for this application, but I am not saying that it is always sigma for contrast for. Of course, changes from application to application. So this is good. This is good. By playing with this kind of stuff, I can get whatever I want with these parameters. But the problem is this: these corner points, they behave very weirdly like these. Okay, can we do something about the corners? Corners are important. Okay, edges are important to give us ideas about the image. But corners are more important because they are more distinctive. Okay, so we talk about filtering. Okay, transforming the images from a form to another form, and then we talked about the edges that correspond to sudden changes in the image intensity. Now we are going to talk about the corners. Okay, and corners are more interesting than edges. Certainly, they are. They provide higher level information about our images. Okay, Why do we need to find the corners? If you find the corners in an image, okay, for example, this is a corner, this is blue, use the blue, corner point, corner point, corner point. These are corner points, and sometimes these are considered as corner points too, okay. Using these corner points, I can match these two images, okay. It looks like this one corresponds to this one will correspond to this one will correspond to this one will correspond to this one. What do I get? I get some kind of a registration between these two images. Maybe I can write a homography between these two, right? When you write the homography between these two, I can just put one on top of the other and see if these two things are the same. So maybe a stop sign detector on my car, running in my car's computer, would work this way. Find the corners of the current image and try to match it to the corners of all the previously seen stop signs, and if there is a nice overlap, then you will say that there is a stop sign ahead, so stop the car. Maybe I can do that. Doing such a thing with the edges is more difficult because there are many edges you can see in an image, but the number of corners are small. It's a smaller number. Also, the corners are more distinctive. Okay, so we are interested in finding the corners. Okay, so it's a fundamental application for image alignment, registration of the images between things. Okay, for example, that would be another one. Remember, we have two eyes. Do you remember those? Okay, we have two eyes, two cameras. If I take two images out of each camera, left image and right image, I like to find the correspondences between these two images, and the corners would be a very good candidate to find these correspondences. That's the 3D reconstruction. Okay, motion tracking. If I am a robot, if I am moving in this room, I need to find the correspondences between the images taken at time t1 and time t2, and again, motion tracking. Indexing and database retrieval, object recognition. So corner detection or distinctive point detection or descriptive point detection is something that we like to do all the time. Okay, so this is an example about image stitching, panorama stitching. These are the images taken from the same point with a slightly different camera orientation, and if I know that this point here corresponds to this point, this one corresponds to this point. What else? This point corresponds to this point. You guys see what I am doing here? Okay. These two correspond to each other. These two and these two. And maybe this one and this one. Okay. Maybe these two. So if I get 4 different correspondences, that means there is a homography between these two planes. So if there is a homography, I can know where this pixel would be on this image if this image would be large enough, and that's going to give me this. Okay, I can stitch them together. So first detect the corners, then for each corner come up with a description, like maybe 100-dimensional vector for each one, and compare those vectors with the vectors of the other image to see which one is matching with the other one. Okay, so the local features detection and the finding the description and the matching, whichever gives me the smallest matching distance would be my match, and after that I can just do the stitching. Okay, so I am after something that is distinctive. What do I mean by distinctive? Find a point that is different from the other points in the same image or the other image. Want to be able to reliably determine which point goes to which. That will be distinctive. And an operator that is repeatable. What do I mean by repeatable? if I run the same operator, if I find the corners on this image and that image, I should be able to say that, okay, this is a corner and this is a corner, etc. Okay. This is a good example, okay, for the object detection. If I find these kind of distinctive, repeatable points, maybe I can do the object detection. How do I do that? Okay. Find these corners around this point. Corners, corners, corners, and on the other image too. And if I can match enough of them, then that means that I'm doing the object detection. I can say that if I know that this is a truck, toy truck, I can say that this is a toy truck too. Okay. So our goal is compactness and efficiency. I should do this in an efficient way, and I should find these kind of descriptors in a compact way. I am after these. Of course, this is not going to be very easy, but we are going to start from the kind of a easier operator that can do this compact and efficient detection of the corners, and we will make our way towards the more useful ones. Okay, so if we are going to find these kind of features, corner detection, it should be distinctive, repeatable, compact, and efficient. Distinctive means each feature can be uniquely identified. Okay, it is not just an edge, it is not just a corner, but I have features on it. You can distinctively say that it is this corner. It is repeatable. I can find the same point on the different images, Doesn't matter if the image is rotated, doesn't matter if the image is smaller or larger or a little bit dimmer or brighter. Okay. Also, I am going to do this on a computer, so it should be efficient and it should result in compact representations. Okay. So I am going to first detect those points, then I'm going to describe them, match it. We will first do the detection. That's the corner detection. That's the basic idea. So let's look at this one. Let's say this is my image, bright background and dark object. If I am looking at this window, I am in a flat region. Nothing interesting is happening. If I move left, right, up, down, doesn't matter, I see the same thing. So these kind of places are not distinctive. I don't like these kind of places in terms of corner detection. It's just a flat region. Nothing is happening when I move around. Okay, so that's called the flat region here. When I am on an edge, okay, if I move up and down, again, I don't see any changes, right? I don't see any changes. Everything is the same. Other than this direction, if I move like this or that, I see some changes, right? I see that things are changing. So I call these kind of areas as edges, edge regions, okay? No change along the edge direction. There is a very special direction. That special direction, if I move on that direction, it will not give me any changes. That's called, that's an edge region. The most interesting one is this region. In this region, if I move left, right, up, down, doesn't matter. When I move my window, everything changes, right? Everything changes. Let's look at this one. This image and this image are very similar. They are the same thing. Okay? Also, the black image and the green image are very similar. Okay? So there is a special line, special edge direction that makes all these images almost the same thing. I can't find any directions like this for this one on the corner, because if I move this way, okay, I see that inside my window the corner point goes to the upper left. If I move this way, again my corner point moves. I can't get the same image with different directions. That's why we say that this part of the image is a special part. Any changes in the position of this window will change my final results. So I will call these kind of places as corner positions. I will call these kind of places as edge positions. I will call these kind of places as flat region positions. I am mostly interested in this part, okay? This guy named Harris, they defined an operator that can differentiate between this kind of a place or this kind of a place or this kind of a place. Say that given a window, I will tell you it's a flat or edge or corner, okay? Flat, edge, or corner, and we are going to see how that is one. That's the basic idea. Since I don't have much time, maybe why don't I give you the basic idea? Like, but these are nice, but I will skip. But I will come to them later. Let me show you. Let me show you this. Okay. Like this one. Move it around, nothing changes. Move it around only in one direction, nothing changes. Move it around, whatever you do, everything changes. That's called the corner. Okay? So that's what we are going to do. If I move my window in this direction UV, okay? UV is just two integers, like 1 and 1. If I move it like 1 and 1, so I am adding 1 to x and adding 1 to y. So I am kind of moving 1 and 1 this way, right? Assuming that this is 0, 0. Okay? So for each UV position, calculate this one. For if I am at this position, doesn't matter where I move this window, the difference will be always 0, right? So D00, 0, it is always should be 0 because I didn't move anywhere. D11 for this region is going to be 0. D01 is going to be 0, and etc. But for this region, some of them will be 0 and some of them are not 0 at all. Okay? So I am trying to find window positions, okay, for which this function will behave widely for the UV values different from 0, 0. That's what I am trying to find. So you can say that, okay, let's try all the different UV values starting from minus UV values, for example, minus 3 U and minus 3 V to plus 3 U and plus 3 V. So let's test all the positions and see everything changes. Well, that's too much time, too much CPU time. Let's do it in a more mathematically systematic way, more efficient way. Let's use some matrices. Maybe this is a system of linear system that will tell us something about the directions of our movement. Okay, maybe we can find it later, and that's what we are going to do. At the end, we are going to show you something. Okay, looking at the image gradient values, we will come up with a matrix like this, and we are going to find the eigenvalues of this matrix, and we are going to say that if there are two eigenvalues in this matrix, there is a corner. If there is a single one, then there is an edge. If there are no eigenvalues, then there is a flat region. And next week, I'm going to show you mathematics of this one, of this equation, which is not that difficult actually. Maybe you already saw it. And then after that, we will continue with this case, and we are going to talk about our final goal of sift points, which was a very, very popular feature detector, okay, in 2000s, which will be used for many end applications. Okay, so I am teaching all of this stuff for you just so that you can understand what SIFT is. And SIFT is something useful, even used today. Good, okay, that's it for today. Your homework will be up either today or tomorrow. Okay, good. I'll see you next week.